Morning. Thank you guys for having me. Is the microphone working? Yeah? Okay, you guys can hear me? Cool. Awesome. Yeah, so I co-founded nTopology about 3 years ago with the main goal of basically making design tools more intelligent. And so today, I'm basically going to go through how we approach design at nTopology and kind of what we think of as kind of intelligent design tools. And basically, I'm just going to first go through quickly like some complex modeling methods, both parametric methods, generative methods. Then I'm going to talk about how we represent geometry in Element. So we actually just released our first pro product. February 6th, we did a soft launch. And so that's now on the market, and we have a booth upstairs also. And then I'm going to go through a couple examples of parts that you can make with this geometry. So ribs and cells is two different design methods, basically, and then go through a use case or a case study part. And so when we talk about complexity in design tools, we look at CAD. CAD's been able to produce extremely complex parts for years, right? Like a jet engine is more complex than a person can understand. But if you zoom into the actual part itself, the part itself's geometry is actually not that complex. And the geometry representation really hasn't changed that much since the beginning. We still represent a part by its boundary. We don't necessarily take into account the volumetric space inside of it. And so if you look at nature, for example, nature is kind of the opposite. These are extremely complex assemblies also. But the geometry itself is much more complex. And it's something I can imagine trying to model one of these in CATIA or NX would be extremely difficult, and it would take years, right? And so I think the question we have is, if nature is this complex, how can we kind of replicate that or create design tools to do this? And I don't think the answer is hand modeling or physical modeling. There are methods in the in kind of the market for animation tools that allow you to sculpt and hand model stuff like this. But approaching this from a CAD perspective, a parametric perspective, how can we basically create a design tool that allows us as a human to really understand this complexity? And so there's really two approaches, parametric and generative, that we see. And so, first I'll define those. And so parametric is kind of like a silly definition. I think we say it's making one thing drive another, right? And so certain things are controlled by other things. And so this, again, you have graphs that you can use to tweak and control things. This is generative components like from Bentley in 2003. The animation industry has been doing this also for a long time with rigging and then simulation as well. And then generative is a little bit different than parametric. The way I'm defining generative is 1 + 1 = 3. And so basically the results are more than the sum of any of the parts, right? And so what that means is the rules that you put in are going to produce something that's bigger than what those rules would implicitly create. So one of the simplest examples of a generative process is topology optimization, right? Super simple rule. I have material or I don't have material. Set up some type of loading condition, and then get my shape. Again, topology optimization I think is a pure generative method. I think from the way we approach it at nTopology, we're trying to mix both generative and parametric. And so I'm going to use like a simple example of a bridge workflow and kind of go through, right? Like if you were to model this bridge, you would start by placing a couple of points, then you'd connect those points with a line, extrude that line to make a surface, et cetera, and model that. But if you're going to make this bridge through a kind of parametric and generative approach, right, the first thing we look at are setting up constraints. And so the constraints could be anything that define kind of the space that you're working within. So for this bridge, it would be something like the bridge has to support 200 cars per hour. There's boats that need to go under it, so it has to be a minimum height of 200 feet, and it can't be higher than 1,000 feet. There's a region for a footing a certain distance away from the shore. And so with the constraints, essentially, those aren't quite enough to define a structure, right? You need something else, and that's where we kind of are setting up a rule. And so just to kind of step back for a second, there's a really simple rule. So this is more of a generative approach, right? And this is a rule to make a snowflake. And again, 1 + 1 = 3, so the results are kind of more than just the sum of any of the individual parts. And so the rule here is I'm going to take a triangle and rotate it 180 degrees and copy it. And as you play that rule out through each triangle, you get something like a snowflake. And so you can use this same type of thing for the bridge in combination with the constraints. And so the approach is really for design rules, right? And so in this case, for a bridge, the design rules would be something like, I want to make a truss structure. That truss structure is going to be limited in terms of, it's going to be made of steel. It's going to be some type of repeating pattern of triangles. Has to be a minimum angle and a maximum angle for that truss structure. And it's only really with this combination of constraints and rules that we can then kind of define the whole problem, right? I think if you just set up constraints, you get a very simplistic approach like the topology optimization. And if you just have rules without the constraints, you can just kind of generate anything. It's not clear what exactly can be made, right? And so kind of taking that approach of parametric and generative, I'm going to talk a little bit more now about how Element and the program that we've done and how we represent geometry. Because you need a way of representing geometry to actually play these things out. Otherwise, it's kind of just abstract, right? And so our key kind of 2 ways of representing structures that are different than the traditional way of representing are through a graph and then a volumetric representation, which is this narrowband level set. And so because we're mainly dealing with lattice structures initially, but we can use these for other types of structures as well, we wanted, at the most simple level, to have a really kind of pure topological representation of our structures. So the graph allows us just to represent connections within a structure. And then we can define attributes, either at the nodes, at the beams, at the surfaces. And those attributes can be things like thickness, radius, material, etc. But with the graph alone, it's pretty hard to visualize and see what the structure is. And so the way we can kind of take that graph and extract the shape and make something that you can see and model with is through this volumetric representation. And so the volumetric representation we happen to be using is a narrowband level set, and so it's like a distance field within a range of the surface. And we can go between these 2 representations pretty easily. We can also go from the narrowband level set to a mesh or a boundary representation if you needed to do that to then interface with other programs. And then the way we're editing structures are through modifiers, right? And so modifiers allow us to control things essentially in the program based on the distance to other things, based on certain values. You could import a modifier as any kind of data set, scalar field, vector field, tensor field, et cetera. And so with that graph structure, we actually open sourced that as a file type. It's called LTCX. And we're trying to get this in 3MF. We've been going to the 3MF meetings. And so the goal is to use this really lightweight format to interface with both the simulation side and the build processing side. Because it's much easier, if you know what the topology is, it's much easier to slice that. And it's much easier to run a simulation on that. You don't have to try and make assumptions about the topology from a STL or do any complex kind of intersection checking. And so that LTCX, again, allows us to specify nodes, beams, faces also throughout. It's a really simple XML format. But when you look at these 2 structures, so this is a LTCX representation of the same part. Now, the visualization of the graph is not showing the thickened version. So when you go to narrowband level set, you are seeing the thickened version. But the big difference here is file size. This is the exact same part, even though it's not rendered the same. But LTCX is only 1 megabyte, whereas the STL is 25 megabytes. And so it's approximately 5, depending on the size of the structure, we're between 3 and 5% of the size of an STL for the same exact part. And so again, we think this makes sense to interface. I think STL is a pretty old format. And so this would be a good way. And we're working with other, actually Simulia we're partnered with also at Dassault, and they wrote an importer for Abacus for this format. And then we're talking to the other build processors. And So if we go back to Element for a second, what can we really do with these geometries, right? And so Element today is really focused on lattice structures for 3D printing. I think overall, our goal is to become the design tool for structures that are too complex to model by hand, right? And so the way we define a structure is through a rule. And the rule can define, again, we're focused on lattice structures, so these are repeating structures. Lattices kind of give us like an easy way to test out this like rule-based design process. And so the rules define both a tessellation, so a repeating pattern, and then a unit cell type. And that unit cell type can also vary. And so we have a couple different rules. These rules are based on on beams, so node and beam-based structures. We also can represent like surface-based structures or faceted structures as well. And so the normal workflow through Element when we're generating these parts is you're going to start with a part, or you're going to import your part, right? You probably have like an assembly in SolidWorks or in NX. CATIA, you'll export a part from that assembly and import that into Element. And then you can pick one of the rules or let the program try and figure out what the best rule to use is. Ideally, you'd want to specify like, oh, I want to target density, or I want to target stiffness. And then you'll fill that part up. And so one important thing to note is, in this case, like when you're filling a part that's curved with a repeated, this happens to be a tet-oct tessellation, it's not going to fill the part perfectly, right? Like the lattice is hanging out in certain places. And so there's a couple different ways we can generate conformal lattices. In this version, we're actually pushing on the lattice to push it into position. Maybe I should just take a quick step backwards. Like the way Element Pro works is when you design a structure, we've broken out different tools for designing the topology of the structure from the shape. So the same way we have these different geometry representations, we've broken up the tools into topology generating tools and then shape editing tools. So in this case, right now, we're just generating the topology of the lattice. And it's a node and beam-based structure. It's a little bit more dense. And we can do different optimization processes. We can go through and try and figure out what the best topology is throughout or what the best shape is. And so this is an example. This is in beta. It's not released yet, of a shape optimization process on a bracket where we would go through, or here we go through, and we run a simulation on just the regular thickness. And the user defines a kind of min and max size that could be based on printing constraints or minimum size, maximum size. And then the user can input a max stress, which could be defined by the material. So like for Ti 6.4, it'd be like 860 megapascals or something. And then the program is going to run through and iterate and try and figure out what the best shape is of the beam. So this is after 200 iterations. I think the max stress is like 4 times 10 to the 7th pascals. And then that's going to keep going down. So 1 times 10 to the 7th, 7 times 10 to the 6th, et cetera. And you can see it's changing, in this case, just the shape. It can also run on topology to try and optimize the thickness. And this was a part that we put through material testing. And it's funny because the beam, it was actually almost the exact same beam. It was in that region that broke when we were testing it. And then you would extract a mesh and print it in that case. So here's a couple examples of other types of structures you can do. And so you can pass, this is a part you can pass around that was based on a rib method. And so again, we have different types of modifiers, right? We had scalar fields. This happens to be a vector field that was defined on this part. And we can use that vector field to drive a surface-based lattice, right? And so that surface lattice in this case, it's not, but they could be the kind of principal stress lines, right? If you want to align your surface structure to the principal stresses. And then you would generate a surface lattice that's aligned to that part. I think we were calling it at this point a vector field lattice. And so again, yeah, we generated a lattice. And in this case, the shape, instead of just being round beams, they were beams that that were driven by a certain direction. So in this case, the direction was a surface normal, right? And so at each point, instead of making a beam that was round, it would make a beam that was a rectangle. And that rectangle direction would be the normal of the surface at where it was. And again, you can do it more dense. So there's a metal part going around, which is, it's actually a part of a pressure vessel pipe that this was used for. And so with these rib structures, they're basically, in this case, we're using them so we can reduce the wall thickness for pressure vessels while maintaining stiffness. And this is the part that's going around. In this case, we happen to constrain the vector field based on the printing directions. And so you can imagine if you're making a rib structure and you have horizontal ribs coming out, those wouldn't necessarily be printable in metal, right? So in this case, all we cared about was having a rectangular grid and then just making the orientation in the correct direction. And these type of structures actually happen to convert back to CAD very well. I think one of the big questions in the industry right now is like, how do we take these really complex things and put them back in an assembly or put them back into CAD? And I would say this is probably 10% on the complexity scale, so it's pretty low complexity, and these already start to be pretty heavy for representing in CAD. Yeah, and then so cells. This was one of the first projects we did. It was a paper that was released with Lockheed Martin for a high-energy laser mirror. And this was actually before we had the software built and released. This was like 3 years ago now. And so in this case, we were trying to prove that a 3D printed metal foam was actually more efficient at heat transfer and more stiff than trying to print conformal cooling channels into a high-energy laser mirror. And so there's a couple examples of these type of foams you can see upstairs also at the booth. These foams are also really good for actually medical uses where you're trying to create an implant that has bone growing through it. Has bone growing through it. And so the way you would generate these foams is we have a stochastic module. And again, here I'm going to use a scalar field to drive the density, right? So if you want variable density throughout your part, again, to control that, you would use a modifier. And that you would use a scalar field, right? And the scalar field's values could be target densities. And so here, again, the process is import a part, generate topology based on this modifier, and then generate shape. In this case, the shape is all the same thickness. You could also change that thickness with the same modifier so that the bigger cells had thicker beams and the smaller cells had thinner beams. And then we're not just making lattices, so because of this narrowband level set representation, we can do booleans pretty efficiently with any geometry. So in this case, we're booleaning back that surface. And then, again, so we're approaching this from a CAD perspective. So your model should be parametric, right? So in this case, maybe I didn't want it to be dense in the middle. Maybe that the modifier we needed to change. Maybe it needed to be dense somewhere else in the part, right? And so we could go back, double-click open in the history that node for the modifier, move the modifier up, and then recalculate the entire process. And then it's basically, right now it's not one button click. You could see the yellow warning symbols that show you dirty parts of the tree, so you have to go back and open each one and regenerate it. But that's kind of nice too, if it's a slow process. But we'll have a way of just clicking a button and auto-generating the whole thing. And yeah, you can also generate these type of structures on surfaces as well. Same type of we call it stochastic module. And so again, the rocker arm sample use with surfaces. And you don't have to use the stochastic structure just to extract the edges of those cells. You can also use the cell to place a unit around. So in this case, it's just a beam or a line and make something that's like variable density hairs on a part. And so for a part, we just recently did with SolidWorks this case study for a bike crank arm and SimSolid. One of the big things we found is simulation. Running these parts through simulation is actually quite difficult. And just meshing these parts is usually pretty difficult. And so in this case, we started with an assembly in SolidWorks, extracted the part, opened it in our program, selected this was a custom designed unit in the rule builder, and then generated, we had actually divided the part up in our program. And so we basically said we want a solid wall thickness of 2 millimeters. This part is still in design, actually, and it happens to be way too stiff right now still, so it can be a lot lighter than it is. But in this case, I think it was a 2 millimeter wall thickness. And then we filled the inside of the arm and the outside with a lattice. Now, we're also working with SimSolid, which is a meshless simulation process. And actually, so Ken, who runs SimSolid, this is one of the few simulation methods that we've seen consistently be able to accurately run a finite element analysis on our structures. And so we were testing, this was the original part with the max stress of like 3 times 10 to the 8th. And this was the lattice part. And so this part, I think it was 67% weight savings, but the max stress is 320 megapascals. So if this was printed in titanium with the material going up to like 870 megapascals, our max stress is like way, way, way too low. So we could be way, even more lightweight. And so that's, yeah, titanium Ti64, if it was printed through an RCAM machine and then hipped, it'd be around 800 to 900 megapascals. And so this is still a work in process. I think we have a sample up at the booth. And do you guys have any questions? Sorry, I'm losing my voice also. So. Cool. Oh, I think there is a question, actually. Yeah.
I just wanted, how does it compare with something like topology, a sort of a conventional finite element-based topology optimizer in terms of the weights?
I mean, that's a good question. I think we need to do more research in comparing the parts. I think in this case, you have more control. You, as an engineer, have more control in the process. So we haven't put it up against traditional topology optimized parts. That's something actually we're doing right now. I think in this case, the parts are more editable also by you. So with traditional topology optimization, you're going to set up the simulation, run it. If it doesn't work, you're going to go back, and usually you end up faking the boundary conditions to get something that looks right. And so in this case, you can just manually edit as well as run the optimization process. But I think traditionally these type of parts perform better because it's a higher grain control, whereas topology optimization, it's kind of a very broad sketch of what the part should look like. Is there any more questions? Cool. You can come upstairs and talk to us also later. Thank you.